Hello, my name is Zoe Kanavas. I'm a PhD candidate at the University of California, Davis, where I am advised by Professor Veronica Morales. And today I will present my project, Resolving Flow Heterogeneity as a Graph Theory Problem. Let's briefly discuss the motivation behind this project. While we have a good understanding of uniform flow fields, it is more difficult to predict the spatial distribution of channelized flow fields. As the underlying pore structure grows in complexity, the flow becomes more channelized. In this work, we aim to understand how the pore structure constrains flow partitioning into mobile and immobile flow regions. Let's move to the methods. From a binary porous medium, we have our solid grains shown in black and the pore space in white. We then perform a direct numerical simulation to find the velocity field. Now, we want to divide this velocity field into regions of mobile and immobile flow regions. We first normalized the velocity field by the average sample velocity. Then we classify pixels by comparing their normalized velocity value to some threshold, which we call the percolation threshold. If the normalized velocity is less than the threshold, it is classified into the immobile flow region, shown in blue. If the normalized velocity is greater than or equal to the threshold, it is classified into the mobile flow region, shown in red and white. We initially set this percolation threshold to be at the sample's maximum normalized velocity, classifying the entire pore space into the immobile flow region. Then, we iteratively lower the percolation threshold until a continuous path of high velocity is formed from the inlet to the outlet. This is shown in red and is called the percolating path. With this percolation threshold, we are able to quantitatively characterize flow channelization. Going back to the binary image, we convert the pore space into its topological skeleton. Then we split that skeleton into nodes and edges, where channels are the edges and channel intersections are the nodes. After identifying the nodes and edges, we record the channel geometric information, including the arc length and pore throat for each channel, as well as the node and edge topology. To understand the dependence of the mobile flow region on the pore space structure, we perform a structurally biased shortest path analysis and evaluate how well the path of least resistance predicts the mobile flow region. The path of least resistance has the minimum sum of edge weights of all the possible paths between a source node S and a target node T. We find that defining the edge weights as the ratio of arc length to pore throat provides a path of least resistance that accurately describes the percolating flow path in all structures used in this study. Shown here is a complementary cumulative distribution function, which tells us the probability for a sample to have at least some given accuracy. From these CCDF curves, we can say that our solution, the arc length over pore throat metric, will more accurately locate the percolating flow path relative to our control, the unweighted scheme, which will find the path with the least number of steps. For example, using the unweighted scheme, 80% of the samples would have an accuracy of approximately 0.4. Comparatively, using the arc length over pore throat weighting scheme, 80% of the samples would have an accuracy of at least about 0.8. To answer why paths form at these locations, we look to the network's structural organization. First, we took our graph and separated the edges in the mobile flow region, shown in red, from those in the immobile flow region, shown in blue. Note that the edge width in the schematic is proportional to the pore throat value. This creates two subnetworks. In each subnetwork, we calculated the assortativity, R, to measure the pore throat similarity in each of the flow regions, represented by the variable Rm for the mobile flow region and Ri for the immobile flow region. Here we have the ratio of the mobile similarity to the immobile similarity, Rm over Ri, plotted against the percolation threshold. In this figure, color indicates density. In all cases, the ratio is greater than 1, meaning that the similarity metric R is greater in the mobile flow region relative to the immobile flow region. This tells us that the mobile flow develops through connected channels with similar pore throat values. Also, as demonstrated by the positive Spearman correlation, the Rm over Ri ratio gets larger with percolation threshold, indicating that the contrast in structural similarity between the flow regions grows with flow channelization. Thank you for your attention, and I look forward to talking with you live during my poster session on June 1st from 7 to 8 p.m. Central European Standard Time.